Hi everyone, my name is Anush. I'll be speaking about tiling and parallel processing of large imageries. A little introduction about me. I'm a senior data scientist at Intel. I mainly work on computer vision problems. Our company is an ag tech company. We work on making farming more data-driven. We mostly work on soy and corn farms in the United States. We get imageries from airplane or satellite providers and process those imageries to find problematic areas in the farms and make farming more data-driven. In average, the farms in the United States are around 600 acres. That would be around the same area that is the city center of Yerevan, which is basically not a walking distance. And when you have grown corn that can be higher than the average person in height, so it's difficult to navigate there. That's why the need arises to have aerial imageries in order to get a full picture of the field and what is happening there in general. The main data that we use is about 1 pixel equals to 10 centimeters in resolution, and covering large distances, we get pretty large imageries, so processing that takes a lot of time, and we stumble upon several issues depending on what problem we're solving. Main issues with processing large imageries are, of course, that you would first of all need a machine with a large enough memory to be able to load the entire thing, and if you're doing some transformations, etc., be able to keep all of that as well. And based on that, of course, this also takes quite a lot of time to do. Of course, it depends on the size of the image you're processing and what exactly you're doing, but in our case, it can take up to a day to finish the whole process from start to end. So in this pipeline, we try to optimize as much of the processes as possible. So the solution we came to is basically a divide and conquer one. We try to, instead of solving a problem on an entire image, solve it on parts of the image and then combine all of the results together. We can use raster.io to read any sized tile from the image, given the exact coordinates where that portion of the image is located. So in this way, we solve the problem of having to load the entire thing at once. We can, based on this as well, do it in parallel. So we're again solving the problem of time as well. The issues now arise: how do we correctly combine the results together so that we are as close to the original as possible? The issues we applied this approach to are several. We use it in classification problems, segmentation, and even statistical calculations. Each one done tile level is simple. You just do the same thing you would have done for an entire image, but you do it on a smaller scale. However, the issues arise when we're trying to combine the results, and for each of these problems, the solutions are different, and the problems we stumble upon are also quite different. First off, let's speak about classification, which is probably the simplest one of these three. Let's say we want to classify an image to be either type 1 or type 2. Instead of doing on the whole thing, we do it on the smaller scale and then use simple voting. In this case, we have 9 parts. 3 of them were classified as type 2, 6 of them as type 1, so the entire image would be classified as type 1. In this case, the only problem would arise if we had the exact same number of tiles be classified as type 1 and type 2. This can, of course, arise if you have more classes as well. So how would you classify in this case? For that purpose, we keep also the probabilities for each class, for each of the separate subsections of the image that we're processing. And in the end, we just average out the probabilities for each. In this case, it is highly unlikely that you would end up with two classes having the exact same probability, which is, again, unlikely but possible even if you do any other classification model on an imagery, not just tile level as well. So this solves our problem for classification and combining the results tile level. So to summarize, we just run the same classification model on separate tiles, save the results and the probabilities of each class per tile, and then average out the probabilities to take the maximum one. Next, we came into a problem to be able to apply this to statistical calculations. Basically, this came from one case, which, of course, gave us a lot of opportunities to improve for other fields as well, but the main issue was with one. Just the field itself was so large that just calculating the standard deviation of the entire data was taking, I think, over 10 hours or something, which was crazy. So we tried to optimize that process. The calculations we came up to we needed to do was mean, max, average, and standard deviation. For mean and max, it is fairly simple. You just take the mean and max of each and then take the mean of means, max and maxes, and this will always be equal no matter if you do it tile level or do it on the entire imagery. You will have no loss of accuracy whatsoever in this case. For mean, you have to do like one extra step, just keep the count of each data point in each tile and then calculate the mean based on that. In this case, again, you will have the exact same average result if you do it tile level then combine, or if you would have done it separately. However, what do you do for standard deviation? None of these approaches, you can come close with averaging it out or doing something else, but it's still fairly far. So I found an approach to approximate standard deviation. You can see it on the formula here. We use the averages of each tile, the standard deviations of each tile. I think that it's SDs are standard deviation, MIs are the means of each tile, and NIs are the number of points in each tile. And on the previous example where we had just 50 data points, I think the original and estimated standard deviations are almost identical. However, if, as I said, our problems arise with doing calculations on larger imageries, doing this on larger scale, the difference is much more noticeable in that case. Well, it is more noticeable. In all the examples that we tried to decide whether we want to move forward with this example or not, the most difference we saw between the original and the estimated was around 2%. Below is just an actual example from one of our fields to see the difference of estimated and actual standard deviations. And as we use the statistical calculations to later feed decision trees, we were okay with having this type of small variations because it is unlikely that we would end up with 2% difference that would push it to the other branch of the tree. So this type of error time trade-off was okay for us. And for the example that I was telling you about at the start of this section, we managed to speed up this whole calculation process from 12 hours to 25 minutes, doing it tile level. To summarize, again, we do the calculations tile level. We keep mean, max, count of elements, standard deviation, and average of each tile, and then use this to estimate everything for the entire tiles. Another interesting question we came upon, I think even last week actually, was how to do the same thing for quantiles. how can you estimate quantiles of an entire image without having to load the entire thing at once. We actually found a couple approaches for estimations. These weren't as close as the ones for standard deviations or something else, so I haven't really included it, but that's, I think, an interesting thing to think about. Segmentation. This can apply to any segmentation model, be it machine learning model that does some pixel-wise classification or something else. The thing we came upon when needing this was we needed to generate a map of a given field and do it runtime. So let's say, for example, here on the left-hand side, we have the image of a field. On the right-hand side, we have a generated map of the field with 4 or 5 classes, I think. This is done if we do the same process on the entire field. Currently, our approach is that we have to generate this map previously, keep the polygons that we have, and then when we have to generate this map instantly, we just load the polygons and do some final tweakings there. However, we were thinking of a way that we can do this more flexibly so that any change we do, we don't have to go back and rerun all of the flights, to regenerate the maps on all of the flights where we want to have this map, or be able to do quick changes and see the results instantly and stuff like that. So the idea came to try and do this tile level as well. Let's say this example, by the way, is a small example of the 1024 pixels over 1024 pixels, just a portion of a field, so that I'll be able to show all the details. In this case, we split it into just 4 parts, load each part separately, do the same map generation algorithm that we did for the whole thing. And in this case, as you can see, we have like clear lines, clear stitching lines that are clearly visible. Like this is where the first tile ended, this is where the second tile started. So how are we able to make this process smoother so we'll be able to end up with a map that actually looks like a map, not just several maps stitched together. The idea is to, instead of, if we want to see the 512 over 512 tile, instead of loading that, we load it with a buffer, so that basically that tile is aware of what is happening next to it, what is happening to its neighbor. So we run the same algorithm on a larger tile, however, we still write the smaller one. This means that the first tile we will read with a buffer that is larger than itself. The second one, again, we will read with as an overlap with the first one. This means that each of them is aware of all of the neighbors that are besides them, so the transitions are able to be more smooth. In this case, this is the result we see. Again, these are the same 4 tiles. We just read them with 50 pixels larger, but still wrote the 512 pixels over 512 pixels. You can see here that we still have some distortion. It is not ideal smooth finish. However, this is still better than the previous one where we had them exact lines dividing each tile separately. You can again solve this problem by having a larger overlap or doing some additional smoothing, etc., for in the map generation process altogether. Depends mostly on the problem you're trying to solve. However, for us, the ability to be able to generate any map from given any image instantly is more important than having a perfect map, even though it takes like 10 hours to generate it, for example. So to summarize, here again, we run the segmentation model per tile, but with an additional buffer, save the results from the original tile with the smaller one. Combination is just raster.io gives you the option to, as I said, read from each given tile from each given location, as well it gives the option to write it, and this gives us the option to parallelize this process as well. As a conclusion, we can do tile-level processing in multiple scenarios. This goes for classification, segmentation, even statistical calculations. Might be a lot more scenarios that you may encounter in your day-to-day life. These are the ones that we encountered and were able to solve. Processing tile level helps parallelize the process. If you're dealing with large imageries, it produces faster results. The results aren't always identical, whether you do it tile level or do it on the entire imagery. The way you could choose whether you want to adapt this approach or not is how much you care about the accuracy of your results and how much you care about spending extra money or spending extra time on your processing. In our case, we have our entire processing on AWS machines, so we basically spend money for every additional minute of processing. So being able to parallelize a lot of stuff and do them faster is important for us, and giving a bit of trade-off for accuracy is okay. And in the last approach, as I already said, doing it this way was the fastest way to be able to generate a map on the go for any given image without needing any additional information on that image. Thank you. Questions?
Yeah, is it the only application in agricultural ecosystem, or are there any other use cases that these big data sourcing can be used?
There are other companies that do sort of ag tech stuff. Many are different. There are some companies that provide only imageries and do the processing on those. Some companies that do the exact zoning that I was showing. I think most of these use satellite imageries, but a lot of people are trying to do the same thing.
Are you using satellite images?
We're using both satellite images and airplane images, depending on the sort of area of coverage. Airplane images fly lower, so you're getting better results there. The resolution is higher, so you can see more. I just didn't think to put an example of a field here, but you can actually see the vegetation rows because the resolution is so high. It's clearly visible what's happening on the field. Satellite imageries are lower resolution, more blurry, but you can still get a lot of value out of those.
Do you calculate the statistics on intensities, pixel intensities of the image?
We calculate them per pixel, yeah. Yeah, okay, that's a good question. So there's a vegetative index called NDVI that is used in agriculture. This is a combination of red band and near infrared band that we're able to get due to our sensors. The idea is that when combining these two, you get sort of a scale where the brighter it is, the more vegetation there is, the lower it is, the less vegetation there is. You can clearly identify vegetation rows there. You just go back. This is just not colorized, or you would have been able to see better. However, the brighter areas here are the darker areas here are the areas where you have less vegetation. This spot here is actually just soil, so you have no vegetation there. This sort of blurry, it looks blurry due to the resolution, but these are actually clear vegetation lines, and the map we generate is based on this as well, which will give the farmer a general idea that this part of the field has good vegetation, this part has bad vegetation, and based on that map, they can actually load it into their automated tractors and do some spraying application or some other thing based on the geographic coordinates that we are supplying.
Okay. Can you go back to the slide where you're showing the tiling logic?
You mean here?
Yeah, this one.
Yep.
So when you're leaving some part out of the main tile, then how do you recover the?
Oh, we're not leaving them, we're reading above them. So basically, this is 512 pixels. Instead of reading the 512 pixels, we read like 562 pixels. So we have like 50 pixel buffer here. We do the segmentation on the larger tile here, but then we write the smaller one. If you would have wrote the larger one, you would have still gotten like the line overlap that we saw on the previous one. However, this way we're sort of making them aware of what's happening at its neighbor, but then taking the overlap and just making sure that each of them is aware of is responsible for its own half.
And then you do the same from, let's say, left to right?
Yeah, we do the exact same. So for the first tile, you would read this 562 pixels. For the next one, you would take 50 pixel buffer here, and then also 50 pixel buffer here on the right as well.
So do you just resize and put it on the other, like 512 tile, or?
Well, Raster.io gives you the option to use an offset, so it does it for you. You just basically have to make sure that when you're later on writing the tile, you just take the extra portions out correctly and then write in its correct location.
Yeah, but like, it seems to me there is something missing in those areas where you leave those 50 pixels out.
We don't leave anything out. We read with an overlap. So you would read like a larger portion here and then write the small one. Read a larger portion here, write a small one. They come and meet together at an exact same location. So when writing, you don't overlap the two tiles, but when reading, you read with an overlap, so they're aware of their surroundings. The reason we don't write with an overlap, so you can have like small buffer when writing as well, but it needs to be smaller than the one you're reading from. Otherwise, you would have like, so in this case, we have no, each tile doesn't know what's happening around it, so you have the clear lines dividing the two maps from each other. If we had, like for example, if we read like this and wrote also the larger one here, there would still be some less distortion, but more distortion than if you take out, if you make sure that they meet in the middle and not overlap each other when writing the tiles themselves. Anything else?
Do you also try like, change detection on, like, as I understand, you monitor the same place for a couple of times, like periodically. Yeah. Do you use some kind of?
We do, but probably not in the way you might be thinking of. So again, for performance's sake, we don't load two images from two different times in a timeline and try to compare this. I think we did that at some point several years ago, but we came to our main product for analytics is to generate trigger some alerts, like you have this issue here or this issue there. So the way we use change detection is we generate candidate problematic areas, keep them as polygons and not the entire image, which is more efficient and easier to load as well. And afterwards, at some point in the timeline, when we try to identify if an area is problematic, we look at the areas that overlapped with this one and see what happened there, and based on that decide what's going on. We don't do any examples of map matching change detection, but we do use it in some manner. Anything else? Thank you, everyone.